All righty. Sarah, you want to kick the program off?
Sure. Tonight we have Ben talking about dark matter. A lot of you have probably met him already. He joined us in early 2020, so like right at the start of the pandemic when we couldn't meet anymore. But he's been in all of our virtual meetings and he's on the board and part of the spectroscope team, so he's pretty active in our group, and now he's going to give his presentation. So thanks, Ben.
All right, thanks. I guess I'll go and share my screen here. Okay, you guys can see it?
Yes.
Yes.
All right, great. Okay, let's get started here. So just a brief outline here. Dark matter, what is it? How do we know it's there? And how do we find it? So to answer the how do we know it's there question is we need to talk about galaxy rotation curves and a little bit of cosmology. Then I'll talk about the potential dark matter candidates, what we think they could actually be. So Wimps, machos, and physics beyond the standard model of physics. So how do we search for it? Well, there's pretty much a three-pronged approach there. So accelerator searches, indirect searches, and indirect searches. And my background's all in indirect searches, so I'm going to be talking about that mostly. And so when I was doing indirect searches, I was utilizing gamma ray astronomy and specifically the Veritas instrument. So I'll talk a little bit about gamma ray astronomy. How do we find gamma rays coming from outer space? And then I'll talk about the various places where we look for them in outer space, dwarf galaxies, the center of our own galaxy, various galaxy clusters. And then also talk about, excuse me, searching using cosmic rays. And then I'll talk about the future and where things are going, where we might someday hopefully find some of these things. So just a brief introduction on why I'm talking about this. So my background is in physics, bachelor's degree in 2004. And then at Purdue in West Lafayette, and then continued doing PhD there, where I worked on the Veritas program. So I spent a year, and this is this photograph of me in Arizona. This wasn't taken in 2007, it was later on, but I spent the year 2007 on the site, actually working on the telescopes. And that was really exciting because that was the first year of the full array operations. I'll talk about that in a bit. But you know, at the same time, I couldn't just work on telescope hardware all the time. I had to figure out a PhD topic, and it was a little bit all over the place. So I thought about doing dark matter back then. I looked at Lorentz invariance, which is a way to possibly break Einstein at very high energies. Yeah. Black holes, you know, all sorts of interesting things, but eventually I settled on pulsars and pulsar wind nebula, and I did enough work there to finally get a PhD out of it. After that, I worked at a postdoc at Argonne National Laboratory outside Chicago, where I continued to work on Veritas and the upgrade, but I shifted my science focus from pulsars into dark matter, and they made me chair the astroparticle dark matter program. I continued. I was enjoying it so much that I just kept going. So in 2015, I started at McGill University, where I wrote a few papers on that. So about dwarf galaxies and then cosmic rays. And then at the end of 2018, I decided it's probably best for myself to move on for various reasons, which I'll go into. But I left McGill and I stepped down, and then I spent pretty much 2019 being an unemployed bum for the most part. I moved back in with my brother who lives outside in Indianapolis. I was doing some physics, math, and astronomy tutoring. Just in case anyone has kids or grandkids that need help in those areas, I'm willing to help. But in 2020, I decided it was time to get a job, and moved to Fort Wayne and started with L3 Harris. And actually, my 1-year anniversary with L3 Harris is tomorrow, so it's been a year. I would say it'd be a great year, but with the pandemic, you know, it is what it is. But so far so good. And I got to meet all you lovely people. So let's talk about myself and talk about masses of galaxies. So this, the mass of a galaxy can be inferred from the velocity of the stars that orbit around the galaxy that make up that galaxy. And I promise you, I'm not going to bog you down with a whole bunch of equations here, but this is kind of an important one. So if you remember first year physics, if you take the gravitational force of the stars orbiting the black hole and equal that to the centripetal force surrounding it, you get this relationship for the velocity of the stars going around it. So it goes essentially as 1 over, it's related to the square root of the mass divided by the radius, where the radius is the distance from the center of the galaxy out to where the star is. And then, so from that relationship, you can figure out what the mass of the galaxy is, where m in that equation there is the mass of the galaxy. So, and this is all from Newton. This is, you know, hundreds and hundreds of years old. So if the mass, so with the assumption that the mass of a galaxy is concentrated in the center of a galaxy and that Newton is still right, then the velocity of the stars around it should be related to 1 over the square root of the radius from the center of the galaxy. But what we found, actually, this is not actually the case. So this was discovered by Vera Rubin in the 1960s, which that itself is a big deal because she was a woman astronomer at a time when there weren't too many women in astronomy. But she was critical in finding this missing mass in galaxies. And so you can see in the plot here that it's kind of flat, actually. So if this is the radius from the center of the galaxy, and this is the orbital speed of the star around the galaxy, you expect something like this Keplerian orbit. But what the data actually shows is it's something kind of flat. So there's 2 major conclusions that we can draw from this, and that's that the mass of the galaxy is not necessarily concentrated in the center of the galaxy, and that galaxies are much more massive than what we originally thought. And this is what we call the missing mass problem. So, these rotational curves here. So you have the distance from the center of the galaxy plotted with the rotational galaxy here on the y-axis. So the implication from these rotation curves is that this missing mass is a dark matter. But I should say, and I'll just point out because addressing the controversy here, is that it's also very possible that gravity doesn't work the way we think it does, so that, maybe Newton was wrong. And of course, we know that Newton wasn't always right because Einstein in general relativity, but that really is talking about faster things. And where these stars are really kind of, relatively speaking, pretty slow. But it's possible that gravity doesn't think the way that we think it does. So these are called modified gravity theories, or MOND for short. I should say that most MOND theories have been eliminated experimentally, but not all of them. So there's still MOND theories around. So it's still possible that everything I'm about to say is wrong and that dark matter is actually modified gravity. But just for the rest of the talk, we're just going to assume that dark matter exists. So if dark matter exists, then it interacts gravitationally, but not electromagnetically, because we don't see it. We don't see a whole bunch of extra stars or anything else. We don't see light, so we don't see any electromagnetic interaction from it. We just see what gravity does to it. So therefore, that's why we call it dark, because we see no light from it.
And Ben, I have a quick question.
Sure.
Does dark matter act the same way with gravity as regular matter?
That's the underlying assumption, yeah.
Okay, that's it.
Yeah.
That's my question.
Yeah, okay. Yeah, I should say that if anyone else has, questions throughout the talk, and if I'm going too fast or something's not clear, please feel free to interrupt me. So we know. So just a quick introduction to cosmology, because cosmology is not really my field. But the composition of the universe is basically in this pie chart here. Nice little arrow pointing out where we are in all this. So, but we know from the measuring the redshifts of galaxies that the universe is expanding, and you can sort of think of that as a balloon. That's the popular metaphor for that. And we know that the rate of that acceleration is speeding up. And so we know that these things are happening, but we don't know why. And this is dark energy. So this is the big part of the pie chart here, is that the galaxies are pushing away from each other, and we don't really fully understand the cause of why that's happening. And then we know that from this that we can infer that dark matter is about another 26% of this. And so so the universal composition, so everything that we are, everything that that we think of baryonic matter, so atoms, stars, planets, us, that's only 4%. So take that in for a second. So this is the stuff that keeps me up at night. Is 96% of the composition of our universe is not well understood. So we have this 26%, which is dark matter, and 70% of dark energy, which we have less of a clue about dark energy than we do about dark matter. I'm going to be focusing about this 26%, but we also have the 70% where we have no idea what's going on. And so you think about it, everything we know is in this 4% of this pie here. So, that's a big takeaway for me. That's, the kind of things that keep me, up at night staring at my ceiling. Okay, so let's get into the dark matter candidates. So what is dark matter actually composed of? And the spoilers is we don't know for sure. But we could say that dark matter falls into two possible categories. So machos, which are massive compact halo objects. I don't come with these acronyms, but they're great. So these are things like black holes, brown dwarfs, neutron stars, unassociated planets. So essentially these things are big, they're kind of compact and dark. They don't emit a whole lot of light from it. Many theorists nowadays think that machos alone, they think that machos make up a percentage of dark matter, but not by themselves. Like machos alone cannot fully explain all the dark matter that's out there. So the other major category is Wimps, which stands for, which is the title of my talk, weakly interacting massive particles. So these are particles that are massive but don't interact electromagnetically. Therefore, we don't see any light from them. So the only interactions that we can see through them is through gravity. So so we're talking about particles here that are affected by gravity, but they're not affected by anything else except for possibly weak nuclear forces. So I'm not going to talk about machos much from here on. I'm mostly going to be focusing on Wimps. So Wimps apply physics beyond the standard model of physics. So what's the standard model of physics? Physics, the standard model is essentially this chart here. You could think of it as, if you remember from chemistry courses, the periodic table. So this is essentially a more fundamental version of the periodic table. This is essentially a periodic table for the different type of particles out there. And this was developed back in the 1970s, and it's been hugely successful in predicting particles that we hadn't found at that point, and then we later on discovered. The latest being this Higgs boson back in 2012. But if a WIMP should be discovered, that would be evidence for physics beyond the standard model. So that's a big deal. So and there's you get a good particle physicist theorist, and they'll come up with a whole bunch of different ideas of what it could be. So there's a proposed type of WIMP called a neutralino, which exists in these supersymmetry type models. And these particles would be essentially their own antiparticles. So you think of matter and antimatter, and they meet each other out in the universe, and they would collide and annihilate each other. Essentially, if two neutralinos were to meet out in space, they would collide and they would self-annihilate. And then they would, when they self-annihilate, they would create something, and they would create standard model particles. So something off this chart here, that would be something, and then everything here is stuff we found before. So this is stuff we can actually look for experimentally. And I should also say that it's also possible that these neutralinos could also decay. Sometimes particles decay, and when they decay, they could form standard model particles that could also be observed experimentally. How am I doing so far? Have I completely lost everybody, or are we doing good?
Yeah, doing good.
Okay. No questions so far?
Well, my only question is, if these neutralinos are decaying, since you asked, when they hit each other, how can there be a lot of neutralinos around? Because they would run into each other and
yeah, that's an excellent question. So the decay lifetime of the neutralino is very long. So we're talking, so I mean, I'll go back a slide here. So a lot of these particles that are unstable on the standard in the standard model, they're maybe stable for only like a few minutes or a few seconds, or in some cases like a few microseconds. But neutralinos are supposed to be stable for many, many millions of years, billions of years. So they would decay, but the decay lifetime would be long, almost, the lifetime of the universe so far, since going back to the Big Bang, basically. So,
well, what I meant was that if there's a lot of them to account for your missing matter, who cares if they exist, if they can hang out by themselves for a long time? Wouldn't they basically run into each other and then make, you can't, it's
why
like
haven't they?
You go into a neutralino bar and there's like nobody there.
Right.
So
yeah, okay. I understand okay, I think I understand your question then. So basically they don't meet up in space very often. So they're kind of slow moving. And because they're kind of slow moving, they're kind of in space, and they're kind of separate from each other. And keep in mind that we have dark energy that's causing the universe to get even further apart from each other. That spreads them out quite a bit. And so they're spread out, and they're kind of slow moving. So they don't meet up in space with each other too often.
When you say they're slow moving, what do you mean?
Well, slow moving, I guess, in my terms, I would say non-relativistically. So nothing close to the speed of light. I would say maybe on the order of like tens of kilometers per second, which from our point of view, that seems rather fast, but for a particle, that's pretty slow.
So
what makes them move so slowly?
There's nothing pushing on them. There's no forces acting on them. So, it's essentially gravity moving them, and that's it. And gravity moves kind of slowly.
Okay.
So, Ben, could these neutralinos exist around any ordinary particles like what we're aware of?
Yeah.
Or would they self-destruct?
In fact, that's something I'm going to address here in a few minutes. But it's very possible that dark matter is passing through us right now, and we don't even know it.
Okay.
Ben, I got a question.
It's passing through us all the time, and we don't know that either.
It's very possible, yeah. Yeah.
Ben, I got a question. So with the universe expanding, does dark matter go along with that? Is dark matter?
That's the idea, yeah. Yeah, it's believed to.
Okay.
All right. So I'll move on to so we're getting into less theory, more experiment now. All very good questions so far, I gotta say. So there's a three-pronged approach to actually search for WIMPs. So this is a simplified, in particle physics, it's called a Feynman diagram. These arrows, you can think of the arrows as the movement of time. So if you're looking at it this way, time's moving this way. So there's this three-pronged approach. So there's the collider detection, and you can think of the arrow time moving this way from left to right there. So you have two standard model particles going into it, new physics, whatever that may be, and then you have dark matter coming out of it. So essentially with colliders, you try to actually make dark matter. Then you have direct detection, which is something Peter was kind of getting at. And that's, you have these standard model particles and you have dark matter coming into it and they scatter off each other. And so then you look at the standard model particle as it bounces off the dark matter. And then you have indirect detection, which is my area, where we have two dark matter particles that meet each other in the night. New physics happens, they annihilate, and then you have standard model particles coming out of it. And so this is what we actually try to measure. So with the accelerators, the accelerator searches are basically dominated by the LHC and Geneva, Switzerland. So this is essentially, look at this ring here. So this is the largest particle collider in the world, 27 kilometers circumference. And so why is it so big? So the reason it's so big is that the larger radius you have, so the larger collider you have, the higher energies you can accelerate your particles to. So, and then, so because you have Einstein equals mc squared, the higher energies you can accelerate your particles to, that means the more massive particles you can look for. So since we're looking for something that's massive, we're looking for these massive particles, you want the biggest collider you can possibly get, or well, in this case, actually afford. Keep in mind that this is a worldwide effort by, not just the United States, but several countries around the world, all getting together and contributing to this. So I think, I think if you talk to any particle physicists, they try to build a bigger one if they could afford it. So you accelerate these protons in the LHC up to as close as you can get to the speed light as you can, and then you smash them into each other, and then you smash them into each other, and you got all these interesting products that come out of it, and then you look for what's not there. So you look at essentially missing momentum coming out of it. So, and then the missing momentum coming out of it is what we think dark matter could be. So we would get essentially these missing momentum or missing energy coming out of it. And this missing energy would become the mass of the dark matter particles.
Hey, Ben, what percentage is missing? Does it kind of correlate with your pie chart you showed earlier?
I'm not sure I understand.
Well, you said the momentum.
Oh. Yeah, go ahead.
Yeah, I think you're catching on. You said because there's missing momentum and your search is based on that. What percentage is missing when you smash particles? What percentage is missing? And does that have any correlation with your pie chart that you showed earlier about the mass?
So the pie chart is kind of casts a wide net. So essentially there's a wide range of masses we can look for. So because there's uncertainty in the pie chart, and there's various, essentially this also depends heavily on the models that the particle physicists come up with. So so with this, even with the largest particle accelerator in the world, we still can't get to the highest masses. We still kind of probing the low mass range with that, but we can still get some very interesting results out of this. And then I should also say that I believe they're still working on upgrading this, so they try to push it even faster. So you push the particles even faster, you can actually probe to even higher masses.
So when you said there's missing momentum, does that equate to a certain percentage that is missing that you don't know about? What happens when you smash particles and there's missing momentum? Is that pretty much happen all the time? There's like 74% is missing that you don't know about, or?
Well, it would be no. Let's see here. So we're very close to the speed of light here when you're crashing these particles into each other. And so far, no missing mass has actually been found, at least at the sort of lower mass range. So the higher you can push your particles, the more higher range you can look at. And so essentially at the low masses, I think we found as good as we're going to get. So if you can accelerate your particles even faster, then you can maybe get up to the higher masses.
So it's going to take a bigger collider.
It's probably going to take a bigger collider, yeah.
So this missing momentum is just a theory. We haven't found any yet.
We have not found any yet. You're right.
Okay.
Direct dark matter searches. So this is when you have dark matter coming in. As I talked about earlier, you have dark matter possibly passing through us right now as we speak. So these are Wimps that would be recoiling off of standard model particles as Wimps travel through the Earth. So how would you actually look for that? So you get these particle detectors deep underground, and essentially you get a big vat of stuff. You get a huge mass target, and you fill it with a liquid noble element. So like something like argon or xenon or something like that. And you cool it to really low temperatures, and then you use that as essentially as what your target is. And so you look for any possible particles coming off of that, and then bouncing off of the neon or the argon or xenon, what have you. And you would see, essentially you would see the ricochet, and then you see the light come off of that, and then you would be able to hopefully measure that. And it should say that there has been a signal that has been found by one experiment, Dama Libra in Italy, which they claim is due to a dark matter signal. But one thing is in science is you want to be absolutely sure before you make extraordinary claims like we've discovered 26% of the universe or what have you. You want that essentially verified by other experiments, and so far that has not happened. So far, other experiments have not been able to verify the Dama Libra signal. So that's a very interesting area of study. Is this Dama Libra signal real, or is this something maybe wrong with their experimental setup? And so that's still very much an open question.
Hey, Ben,
Yeah.
Going back to that, so it looks like your detector, you're assuming, or you're basing out this on electromagnetic based detectors, right?
Right.
So has anyone tried using other forms of, I guess, the fundamental forces detectors, whether they be gravitational or something else other than electromagnetic? You might be looking, you're assuming the interaction and the ricochet is going to be electromagnetic based, and maybe it's not.
So, all right, I should back up here because the recoil itself, I believe, So the recoil is actually due to, I believe, the strong nuclear force. And then because of the strong nuclear force, there's a interaction that occurs that causes to be electromagnetic in nature. So we know that we don't see light from dark matter, so we can pretty much eliminate electromagnetism right off the bat. Now, so this is technically speaking strong nuclear force here, what we're seeing here. Weak nuclear force, that's decay basically. So that's something, so by weak nuclear force, that's essentially the decay stuff with the indirect detection methods, which I'm going to be talking about here in a few minutes. Gravitationally, that's an interesting question, because maybe, I've been out of this field for a few years, so maybe with the, drawing a blank here, the gravitational wave detectors, LIGO and experiments like that, LIGO, Vigo, maybe we could find something with that. I don't know.
Yeah, I thought that'd be kind of cool. Yeah, thank you.
Yeah.
Ben, I had a question. With that type of detector, what do you have to worry about detecting that's not dark matter? I mean, stuff like gamma rays, or is there stuff that causes problems?
So each of these different types of experiments have their own different backgrounds that you have to worry about. That's a really good question, actually. So for direct dark matter searches, the biggest background, I believe, is neutrinos. So neutrinos are very small, light, possibly even massless, called ghost particles. And so what will happen is they'll bounce in and they'll cause the same sort of ricochet type effect. So if you look at this curve here, this kind of shaded area here, that's the area that's been eliminated due to neutrinos. So neutrinos for direct searches, I would say, is probably the biggest background you have to worry about. For the accelerators, I'm not quite sure what their background would be. Possibly, I would say maybe cosmic rays, probably muons, but I'm not too sure about that one.
Thanks.
Yep. Okay, so indirect dark matter searches. So this is looking for dark matter in space, because everything sounds cooler when you say in space afterwards. So as Prilly mentioned, that dark matter can annihilate or decay into standard model particles, which could be, which you can look for with existing experiments looking out in space. And so the particles in the standard model, as I showed a few slides ago, they're actually very diverse. They're very diverse lot. That's I say that standard model is 4% of the universe, but it's very complicated 4%. So because the type of particles out there are diverse, so are the detectors that are designed to find them. And just a few examples here. So you can look for using cosmic rays, and one experiment that's done a really good job of that is it's called AMS, which is the Alpha Magnetic Spectrometer. I believe I got that right. Hopefully I don't. Hopefully I did. Which is on the International Space Station. So it's this little, I shouldn't say little, it's maybe like a meter or so large. That's on the International Space Station. That's used to find dark matter from cosmic rays. Neutrinos, which is big player in that right now, is IceCube in Antarctica, and this is literally at the South Pole. It's like maybe a few hundred meters away from the South Pole. And so what they did is they drilled these large holes in the ice here, and they're like 2 kilometers deep here. And they put detectors out there, and it's kind of similar to the direct experiment, where you have like essentially you need a big area of stuff in middle. So they use ice as their medium there. So you have ice in Antarctica, and so you have neutrinos passing through the ice in Antarctica, and so they're trying to pick that up, and they've been very successful at that, I should say. And then where I'm going to be talking about is gamma rays. So this is Veritas in Arizona. And then I'm going to send the slides to Sarah at the talk, and then I have links here to these super experiments if you want to know more about them in particular. So why gamma rays? I've been talking about gamma rays quite a bit. Why do we care about gamma rays? So the Wimps could hypothetically annihilate or decay into standard model particles, and then you get different particle physicists and they have different ideas. And so there's various different products that could come out of it. So we're not sure which standard model particles that would come out of it. However, the standard model particles, ultimately, many of them would produce photons as a byproduct of these reactions. And so it's also possible that dark matter may annihilate or decay directly into gamma rays. So Wimps are massive, so from E equals mc squared, so they have a lot of mass, therefore they have a lot of energy. The products coming out of them are energetic, and therefore the light that's produced, the photons produced from them are very energetic. And the most energetic form of light there is are gamma rays. So gamma rays is a good place to look for dark matter from these from the byproducts of the standard model reactions, the annihilation and decays that come out of it. So gamma ray telescopes. So there's the current generation right now, early 2021. There's three main types of these telescopes. So the high energy, so from about 10 MeV, so I'm going to be talking about MeV scales and GeV scales and TeV scales. And so just a reminder for everybody, green light, so visible green light, has an energy about 2 eV. So we're talking about light here that is millions to billions times more energetic than what we see in visible light. So various high energy, so and the MeV scale, so millions of times larger. There's Fermi Lat. Here's a picture of the Fermi Lat Space Telescope, and so these are space-based, and it uses a pair production technique to find gamma rays. Veritas, which I'll talk about more details. So we're talking at the GeV scale. So this is we're getting to the billions now of Haas, Magic, and Veritas are essentially the big three players in the field right now. And so these are ground-based telescopes, and they use an air-Cherenkov technique, and I'll talk about what that is here in a minute. And then you go into higher energies, so we're talking tens of billions, tens to hundreds of billions. Ultra high energy, so Hawk in Mexico, this is on a mountaintop in Mexico actually. Hawk and Lasso, which Lasso's in Tibet, which are also ground-based, and they're water Cherenkov. These are actually giant water tanks here. So VHE Ray Astronomy in 2020. So so to give you some historical background here, I started with Veritas about 2004, 2005-ish. And so this is essentially the current map of the number of VHE sources out there. Each of these dots here on this chart here is a different VHE source. When I started in about 2004, there were only like 5 of these dots. There weren't too many of these dots there. So all these dots here have been discovered in the last 10 to 15 years. And going back to 1989, which is 1989, not that long ago, that was when the first detection was, and that was the Crab Nebula, and that was in 1989, done by the Whipple Telescope in Arizona, which has unfortunately been decommissioned. So now the catalog is huge, over 200 sources of all different types of objects. So there's active galaxies here, there's pulsars and pulsar nebula. I talked about doing my thesis on that. Supernova remnants, starburst galaxies, and then there's some of these gray ones, we don't even know what they are. We just know they're there. And then quasars, if you're interested in quasars, we found some quasars with this technique. So just a lot of stuff out there in this at these very, very high energies. So these are essentially, this is a map here of essentially the most powerful objects known in the entire universe. So I talked about a little bit about Cherenkov radiation to actually detect these things. So this Cherenkov radiation is essentially a sonic boom for light. So this is you have an energetic particle that's traveling faster than the speed of light that produces this cone of light that gets detected. Now I should say that we're talking about the speed of light in a particular medium here, that being that water or air. Nothing can go faster than the speed of light in vacuum. Nothing so far, according to Einstein. But faster than light in a particular medium here. So here's a picture of Cherenkov radiation, this bluish glow given off a nuclear reactor. So Cherenkov radiation is very much a thing that we see on Earth in nuclear reactors. And we also see it from these particles coming from outer space. And we can use that. Essentially, they give off these flashes of UV and blue light that only lasts a few nanoseconds. But we can use that to actually astronomy with these little blue flashes. So gamma rays will interact in the upper atmosphere, and they create these electron-positron pairs. And essentially, those electron-positron pairs will create more gamma rays, and the whole process sort of repeats upon itself. And so from one TeV gamma ray, you get about 1,000 particles coming out of it. And each of these particles are giving out Cherenkov radiation. So these are something that could actually be imaged. So here, for example, is a gamma ray, and here's a proton. And you can see that they produce on cameras. Imagine you taking this sort of ellipse and just putting it in 2 dimensions, and you get sort of this light spread here from the Cherenkov flashes. And you can see that the gamma rays kind of compact where the protons kind of spread out a bit. And I should say that the cosmic rays are actually a big background, source of background for us. So,
excuse me.
Yeah.
Go back that one slide, previous one. So on the left, you're saying one particle comes in and it starts generating into dozens and dozens of additional particles.
Hundreds and hundreds, I'd say.
So are the newly created ones less energetic than the one that?
Yeah.
Okay. All right.
So you're right. You're getting into conservation of energy arguments.
Right.
So each of these products and essentially that's why it peters out. We don't all get, we aren't poisoned from gamma rays already. The whole process sort of peters out while still in the upper atmosphere. So each of these generations of particles, each one is going to have less energy than the one that came before it, until the whole thing just kind of peters out, basically.
Yeah, and that's probably a good way to.
That is a very good thing for all life on Earth as we know it. That's a very good thing.
Yeah, I was gonna say lower and lower energy is a good thing.
Yeah. We do not want these things hitting us.
And also, just going back, for false hits, are cosmic rays ever bothersome to you guys?
Oh my God, yes. Cosmic rays are the biggest source of background we have by a very significant margin.
Okay, I was wondering how troublesome they were.
They are very troublesome for us.
Yeah, because
so essentially, I don't remember exactly what the ratio is because it's been a few years since I thought about it. But I'd say for maybe one gamma ray, for every one gamma ray we found, we may find tens of thousands of proton cosmic rays.
Okay, I was wondering about that.
Yeah. It's a big problem for us. Well, for my former colleagues, I say I don't do this anymore. So you have, so essentially, this is an image here of one of our cameras. This is actually a simulated camera right here. And these images are roughly elliptical here, and then we superimpose the images. So each of these ellipses here is from a different camera in the array, and you superimpose them, and you essentially fit ellipses to them, and you can, where all the points intersect here, this is where we can transpose this so we can find out where in space the gamma ray actually came from. And so you you talked about backgrounds for us. And so if you want to help, we actually, Veritas has a citizen science project called Zooniverse. So protons is one type of cosmic ray background. Muons are another. And muons create these sort of rings and arcs in our cameras. And so if you click on this link, it takes you to a place where you can actually hunt muons in Veritas data, and you can actually help train AI and machine learning algorithms to better pick out muons.
Wow, that sounds cool.
Yeah, it is cool. Yeah. Yeah, and I mean, it's essentially, it becomes like, you know, any sort of game, you know, you play on your phone or your tablet. So so you can actually do something like this, and you know, you can you know, a way to kill time and help science at the same time. And I should say that Zooniverse does more than just, you know, this gamma ray muon stuff, but they do all sorts of really cool things with like zoology and all sorts of branches of science. So not just astronomy. All right, so I'll talk a little bit about Veritas. So Veritas stands for the Very Energetic Radiation Imaging Telescope Array System. So it consists of 4 telescopes here south of Tucson, Arizona, about 40 miles north of the Mexican border. So we get visits from Border Patrol and all sorts of things having to deal with that. The full array started in 2007 with a major, and I said I was there at the time, with the major upgrade that was completed in 2012. I also had a hand in doing that. The field of view of the array is about 3.5 degrees. The energy range is about from 80 GeV to about 30 TeV with an energy resolution about 20%. So, you know, an error on based on what energies we can actually measure. The angular resolution is about 0.1 degrees, and I know, you know, this, you guys are probably saying 0.1 degrees, isn't that terrible? Point spread function is not terrible angular resolution. Actually, since this is, you know, for telescopes of these types, 0.1 degrees is actually pretty good. So here's a picture of the collaboration. So the collaboration consists of scientists from the United States, Canada, the UK, Germany, and Ireland. And this is a photo. I'm in this shot here somewhere. This is a photo from when we celebrated 10 years of operations back in 2017. So the telescope hardware. So each of these telescopes consists of 500 photomultiplier tubes that consist of a camera. So here's one of the photomultiplier tubes, and then they're all in this box here, basically. And then there's a 10-meter reflector, which is composed of 350 smaller mirrors. And then, so signals, you know, bounce off the mirrors and go into the camera and get routed. The signals from the camera get routed into here, which is our data acquisition system, where the signal actually gets digitized and we can actually, you know, do science with it. This is me, picture of myself. This is back in 2011, I think, with a crowbar, ready to smash something because I woke up very angry that day. Me hard at work. Here's some astrophotography from the Veritas site. I thought you guys might appreciate seeing this. This isn't taken by me. This is by Moritz, who was a graduate student at the time. So the skies in Arizona, I don't know how many of you have actually been there or not, but it's actually just absolutely gorgeous out there. Skies are just really great for viewing. So you get a very nice view of the Milky Way here. Shooting stars, very nice views of Saturn and Mars here. Here's another one, 2 of our telescopes, old trailer here. So with Arizona, and this area, Arizona is very remote, so there's not too many lights bothering us, although the area is getting built up, so light pollution is becoming an increasing problem. And then here's just some photos I took off my cell phone of the various wildlife and the various critters you would find at the site. Here's actually a brown bear that tried to break into the observatory offices. And it was a very cute baby brown bear, but we're like, oh crap, where's mom, you know? So we just kind of let that be. Bats, frogs. Actually, I was kind of surprised to find frogs there. You wouldn't think you'd find frogs in a desert, but during the monsoon season in Arizona, they do come out, and they like the water, they like the moisture. So this is them close to one of our AC units. Lizards and of course tarantulas. You find tarantulas all over the place. Scorpions too. I'd used to have, when I lived out there, I'd have scorpions in my office. I'd have to take them out every now and again. So, all right, back to it. Back to dark matter. Where do we actually look for it? Dwarf galaxies. So these are smaller, dimmer satellites of the Milky Way, basically. And so each of these places that we actually look for it, there's kind of a pros and cons to each of them. So the pro of a dwarf galaxy is that there's not much of an astrophysical background. So we have no reason to think dwarf galaxies would produce dark matter on their own, or produce gamma rays on their own, I should say. But they're also very massive and compact. The con is that there's only a few stars in them, in some of them. This is one, I think this is Ursa Minor, and the Ursa Minor dwarf galaxy. And I think this one has a few hundred, but some of them only have like a dozen. And so because you have only so few stars, it makes the concentration of dark matter really hard to predict. So there's about 2,000 known dwarf galaxies, and they're not all created equal. I think I'm running short on time here, so I'm not going to get into too much detail about this, but essentially they're not all created equal. So essentially we do the same sort of missing mass product for them, and we try to predict how much dark matter density they actually have. And so that goes into what we call the astrophysics of J factor. This is related to dark matter flux. And so the higher J factor, the more likely we are to find dark matter from it. So we want to look at as many high J factor dwarfs as we can. The problem is that the J factor is kind of not really, depending on which papers you look for and which observations you look at, the J factor could vary by quite a bit, order of magnitude or more. So Veritas find dark matter? No. Spoilers, no. But in the absence of finding an actual signal, we can actually place physical limits on what dark matter annihilation could be. I won't discuss this plot in too much detail, but here's the mass, the predicted mass of the dark matter particle plotted along the x-axis here. And this is the annihilation cross-section. So think of this as like the probability of dark matter actually showing up. So we would actually expect dark matter to be somewhere along this dotted line, or this solid line here. And so we eliminate basically any scenario that's up here, or in the case of lines down here. And each of these different lines on this plot here is a different standard model particle. So, we assume that the gamma rays we would see or don't see, say, annihilate into, say, B quarks. And so this is the exclusion region we would get from that. So we would exclude anything from up here. Unfortunately, we're trying to get down here, so we're still quite a ways off. Dwarf galaxy, so that's one area we can look. Galactic center is another. So the center of our own galaxy, which is the big pro of that is it's very close by. And we think that there is a lot of dark matter located in the center of our own galaxy. Why should our galaxy be any different from any other galaxy, right? The downside is that the galactic center is a very complicated region. There is a lot of stuff going on there. There's various astrophysical backgrounds. Sagittarius ASAR itself is a bright gamma ray source, and there's diffuse gamma ray emission all around the area. So if we find something, a dark matter, or we find a gamma ray signal that we don't understand in this area, it may not be dark matter. It could be something else. And so this is
on that last photograph, is that an actual gamma ray photograph?
No, this is not gamma ray photograph. No, I cheated here a bit. This is Meerkat, which is a radio telescope. So this is actually a radio image of the galactic center here.
So if you pointed that Veritas telescope at that Sagittarius A, would that just wipe out your sensors, or?
No, No, we look, let me just move on here. No, these are the Veritas sky maps of the Galactic Center here, actually.
Okay.
And you can see that, so like I said, the angular resolution of Veritas is not great. So we see Sagittarius A star as essentially this kind of blob. This is a supernova remnant, I believe, that's also nearby. And we also see this as sort of a blob. But these contours here, superimposed here, these are the radio maps. So we have radio contours here superimposed on the gamma ray signal. And as I said, there's a lot of stuff going on here. So we try to, in this map here, we try to say, all right, we're going to look for dark matter here and down here, and then use these areas above and below these sort of arc regions and use that as essentially background signal extraction. And this is still work in progress. So this is still ongoing. So no results to show from that yet. Hopefully soon. So just to kind of hit the point about, so this is what the universe looks like at about 100 MeV gamma rays. So this is the Fermi lat map of the Galactic Center, or the galaxy, I should say, and then right along the middle of the galaxy here. So the Galactic Center is around there. And so a few years ago, it was reported that there's an excess of gamma rays that they couldn't explain. And so immediately people got very excited and saying, oh, it could be dark matter. But to sort of tamper expectations a little bit, they also said, well, it could be a population of pulsars that we hadn't seen before, or it could be the extension of the Fermi bubbles, which are these kind of regions. You can't really see it too well in this graph here, in this map here, but it's these sort of regions kind of above and below here. It could be coming from Sagittarius A star itself, or it could be ultra high energy cosmic rays interacting with dust along the galactic plane. So this really bright red, yellow region here. So this is so the debate, as far as I know, again, it's been a couple of years since I've done anything with this, but as far as I know, this debate is still ongoing on whether or not this excess here is actually dark matter or not. And so the big key takeaway I would say from this is the center of a galaxy is a very complicated place to be. So galaxy clusters, I'm not going to talk about this in too much detail, especially since I think I'm running out of time. Sarah, Julie, how am I doing? Can I keep going, or should I just kind of wrap it up?
Yeah, you can keep going. Don't worry about it.
Okay, thanks. I guess if you get bored, you can just mute me or something. So where else to look for dark matter? Galaxy clusters, so clusters of galaxies. So these are essentially hundreds of thousands of galaxies that are gravitational bound to each other. And so the nice thing about galaxy clusters is that they should be about 90% dark matter. So the dark matter content from them is huge. And I should say this is also not a Veritas or Fermi map. This is just a Hubble image of galaxy clusters, but I thought this was a very nice image, so I thought I'd put it in. And so the cons of looking at galaxy clusters, though, is that they're far away. So the farther away you go, the weaker signal is going to be. And then it's also possible that galaxy clusters could be gamma ray emitters on their own. But Veritas did look. So this is the same sort of graph I showed a few slides ago for dwarf galaxies, only this is for the Coma cluster. The Coma cluster of galaxies, which is about 300 million light years away, and with a diameter of 20 million light years. So Coma cluster is huge. We looked there. I think this is about 20 hours of Veritas data. We didn't see a signal from it. Like the other one, like with dwarf galaxies, we were able to place a limit. So here's the dark matter mass, and then here's the probability of annihilation, basically. And so this limit here is weaker than the dwarf limit by several orders of magnitude. So Just want to briefly talk about cosmic rays because that's another area of interest of mine, and another way you can look for dark matter. So cosmic rays, I've talked about cosmic rays throughout this talk quite a bit. What are they? So these are energetic particles that move through space at high fractions of the speed of light, so very fast, very energetic. So just for example, protons, electrons, heavy nuclei, helium, carbon, pretty much go up the periodic table on that one. So they were first discovered by Victor Hess by balloon flight in 1911. So here's a photo of Victor Hess in a balloon going to go up and discover cosmic rays. Here's a plot of this. So the y-axis here is the flux. So the number essentially over unit time over particular detection area of the cosmic rays, and then here's the energy, and you can see the energy goes from essentially really low to really high. So cosmic rays, essentially the most energetic particles known in the entire universe. And really interesting to me about cosmic rays is that the origins of the highest energy cosmic rays are still unknown, and it's possible that they could be dark matter annihilation or decay products, at least for a fraction of these. And dark matter annihilation and decay could also be used to explain some anomalies that are seen in cosmic rays. I'll just talk about one of these here briefly. So this is the from AMS, which is on the International Space Station. I talked about that a little bit earlier. This is the fraction here on the y-axis of the ratio of positrons, which are anti-electrons, to the number of electrons plus positrons, and as a function of the particle energy. And so this green curve here is what essentially was expected from astrophysics, from all the conventional astrophysics that we know. And then the red here is actually what we observe. So we can actually observe that this fraction's going up. So there's more antimatter in the universe than what we initially expected at higher energies. So more, I shouldn't say all antimatter, but this is specific to anti-electrons. So there's more anti-electrons at higher energies than what we originally expected. And so it's possible that dark matter could explain why we're seeing this red data, such as we are. But it's also possible that, you know, you get something more conventional like pulsars to explain something like this. So I mean, there's lots of dark matter theory papers out there, and there's I mean, there's still a lot we don't know. You know, I guess, you know, maybe a takeaway from this talk is maybe we don't know as much as we think we do. But
Ben, baryonic matter tends to condense due to gravity.
yeah,
Gravity affects dark matter too. So
yeah.
Does dark matter tend in a galaxy like the Milky Way? Does the dark matter tend to condense toward the center of the galaxy, or
Right.
spread out?
That's something I talked about here a few slides ago. So talking about in the galactic center. So that's why we would look at the galactic center, exactly what you're talking about, because it would condense, and where it would actually condense would be at the center of the galaxy.
Okay.
So that's why we look at the center of the galaxy. Good question. Okay, so so this is the Veritas measurement of the cosmic ray electron spectrum, or I'll call it CRE for short. So this is the blue dots here, and the other dots here are from the other markers, are from the other experiments that are out there that are actually trying to also measure this. And you can see this, there's a sort of kink here in our data, not just our data, but other experiments see this as well. This sort of break, and there are, I should say that there are models out there that do say okay, this break here that we don't fully understand could be dark matter. I'm not a big proponent of saying that this kink here is dark matter, actually. I know, like, that's my area, but so I should say everything's dark matter, but it's also possible that this is due to the decreasing population of objects in the universe that can accelerate particles up to those energies. Again, we're talking about, you know, billions of times more energetic than visible light. So you can think that the population capable of accelerating particles to these energies is really small. So I would more likely attribute this break we see in the spectrum here to just a decrease in the number of sources that's capable of accelerating particles to these energies. So I just want to talk just in conclusion, before concluding here, just a little bit about the future of the field, where things are going. A few years ago, before I left the field, we formed the Glory Duck Collaboration. The Glory Duck Collaboration is representatives of the major gamma ray telescopes. So the 3 VHE instruments, so Veritas, Magic in the Canary Islands, and Hess in Namibia in Africa. The Fermi Lab Collaboration, so that's a space-based orbital telescope. And then Hawk in Mexico, we all joined together in this group to see if we can pool our resources and essentially add data from our experiments to each other to try to get a better results than any single one of us by ourselves. And so essentially we're pooling our data, pooling our resources together. Veritas itself has data on 20 dwarf galaxies. So this is increased sensitivity over one single instrument. So we try to get several instruments together to get a better idea of what's going on. And we can do this using a what we call log likelihood methodology without having to share proprietary information of any particular instrument, because we are kind of territorial in that area. The other big future is CTA. So Veritas, as I talked about, is only 4 telescopes. CTA is, there's 2 proposed sites, a northern site and a southern site. I believe they're going to continue building both. CTA North, I think, is going to be about 20 telescopes. CTA South is going to be 36 telescopes, I believe. I may be wrong about that. So essentially, you know, so just get more and more telescopes together to pool more and more of the Cherenkov light, and we can, you know, that 0.1 degree angular resolution, we hope to get a heck of a lot better. And then more telescopes also helps us reduce those blasted cosmic rays that, you know, have been a big background for us. So cut down on that. So CTA in a nutshell, CTA stands for the Cherenkov Telescope Array. So this is essentially the next generation. CTA is going to offer about an order of magnitude greater sensitivity, expanded energy range, and improved angular resolution. CTA consortium itself is huge. It's about 1,500 members, and that's of a few years ago. So it's probably larger than that now. So there's going to be 2 sites and 3 different types of telescopes: a northern site and a southern site. Northern site's going to be in La Palma in Spain, in the Canary Islands. And so that's going to have 4 large-sized telescopes and 15 medium-sized telescopes. I should say that Veritas these are all medium-sized telescopes. So the large telescopes are twice in size and diameter. The southern hemisphere is going to have 4 large-sized telescopes, 25 medium-sized telescopes. Oh, I was way off. I should have said more than 36. 70 of the small-sized telescopes, which are about 4 meters in diameter. So there's various.
What is James Webb gonna do?
Huh?
What does James Webb gonna do for this program?
James Webb, I'm sure we're going to work pretty closely with them. I shouldn't say we anymore. Force of habit. Because CTA is, I didn't get really a chance to talk about this, but because Veritas and CTA are optical telescopes that we essentially overlap in that. James Webb also, in applications for dark matter, they'll help us measure those velocity curves better, so we can get a better idea of how much dark matter is actually out there. And by doing that, we can figure out, where to look. And we better pinpoint which areas of the universe we should be looking at with the telescopes. So there's various shapes and sizes of telescopes in various phases of going on. So essentially, it's very much in the prototype stage right now. This is the LST prototype in Spain right now. Let's see here. SCT. This one's on the site in Arizona at the Veritas site. The MST. This one is in Berlin, actually, which Berlin is, it's a major city, so there's lots of pollution, so you actually can't really do much in the way of actual science there, but this is more prototyping. Actually got to see this one out in person. So there's various prototypes going on, and here's kind of the timeline of the CTA construction. So it's kind of, we're in the pre-production building stages of the first prototypes right now, and so I guess large-scale production is going to start in 2023. This is pre-COVID, so I don't know. That's probably going to push things back quite a bit, I would think. So it may be, so it may be 2023, but it may be later than that.
Hey, Ben, quick question. When you were showing the proposed arrays going up,
yeah,
were they going to be configured as like interferometers to help get that better resolution?
Mm-hmm. Yeah.
Oh, I'm kind of curious. Their physical layout seems kind of weird to be an interferometer. Wouldn't you want more distance between those telescopes than lumping them close together?
So it's really optimized on the size of the Cherenkov light pool, and the Cherenkov light pool is about 100 meters. So 80 to 100 meters is actually what the optimal distance is.
But wouldn't you want the telescopes to be further apart to be effective interferometers?
Yeah, to be effective interferometers, that's true, but interferometry can't talk, is not the primary goal. The primary goal is to get the interferometry is essentially a side effect of something we're already doing anyway, right? So the primary goal of it being a gamma ray telescope array is we want to optimize on how much of the Cherenkov light pool we can actually image. So, and the Cherenkov light pool is, say 100 meters radius on the ground. So that's really kind of what dominates the decisions of putting the telescopes where they are.
Okay, I'm gonna have to.
I mean, yeah, if you want to build an interferometer, you're probably right. You probably want to build them further out from each other. But
yeah, I mean, I'm thinking like VLA and things like that, where you've got
right. And for VLA, you'd be correct, but this is a different type of instrument. So
okay,
different science goals,
And then other, like, this is out of left field, so
okay, yeah, go for it.
Does the world of quantum physics help you guys with this in any way? I know.
Oh my God! Yes. Oh my God! Yes. This is so much of what I've talked about tonight is quantum mechanics. Just to kind of, I wasn't going to go into any, but I mean everything I've talked about with spectra, with the standard model, everything doing with the standard model, it's all built on quantum mechanics. Even the cameras themselves rely on quantum mechanics to understand the signal coming out of it. Quantum mechanics is essentially a very fundamental part of what I mean, essentially it's a tool, right? It's
yeah, that's what I was thinking. It's like,
yeah.
You got conventional Einstein-based physics, and then you got the world of quantum mechanics, and they're so different right now. And I was just wondering
Yeah,
if
I mean, that I could give a whole different seminar on just that alone, on how.
that would be very, very cool, I think.
Okay, well, yeah, maybe talk to Sarah and maybe we'll make that happen. But yeah, the world of quantum mechanics is just very much intertwined with what I was doing for all these years.
That's cool. And then one last thing.
Yeah.
I don't know if I'm going to be able to explain this question, but the thought crossed my mind early on when you said you get so much interference from the cosmic rays.
Mhm.
You were saying like, okay, for like every one that you want to detect, you get, like thousands of cosmic rays and things like that. Could that not be, the cosmic rays be linked to that dark matter? I mean, that may be your.
I mean, that was, and that was kind of the point in what I was saying earlier about, things like this and things like this, where, it's very possible that, some of these cosmic rays have a dark matter origin.
Yeah, I was going to say that it seems to make sense.
The problem is it'd be very hard to say for sure. Because there's also conventional models, just using the astrophysics we already know, from conventional objects of explaining some of these things. But, like things like this positron excess, so we have these features and, less so for the electron spectrum, but this positron excess, this is a cosmic ray. This is AMS, which is just a focused cosmic ray instrument, and they see this thing, this rising positron infection that they don't understand, and they're saying to themselves, well, I shouldn't say that they're saying it. I should say the theorists are saying it for them. They're saying, okay, this rising fraction could have dark matter origin.
Yeah, very, very cool.
Yep.
Ben, I'd like to mention that Bill Wren at McDonald Observatory in Texas has done a very, very elegant job of controlling the light pollution in that region.
Okay. Yeah, maybe I'll pass it along to my former Veritas colleagues, and maybe there's something they can pick up from that. What was that name again?
Bill Wren.
Bill what?
WREN.
Okay.
Ben, I got a question. When you were talking about like the observatory there in Berlin being useless, well,
I would say useless. I did say useless.
Yeah. Okay. Let's say limited. Because of the light pollution, but you're looking for gamma rays that are like so far removed from the way lower frequency photonic spectrum that wouldn't that be like easy to discern one or filter out one from the other?
You'd think so, right? But not quite. So this is what I was talking about, Cherenkov light. So, I mean, I should say that, we don't pick up the gamma rays directly. What we pick up is these Cherenkov flashes that come off of the charged particles from the atmosphere. And these charged particles are blue. These are UV blue light waves, essentially. And so everything, from everything, about light pollution still absolutely applies to the ground-based Cherenkov instruments as well. So not only are the cosmic rays background an issue for us, but also night sky pollution also affects Veritas and other ground-based gamma rays.
So it's not the detection themselves that's being limited, it's your manipulation or being able to analyze the data once you've detected them because of the light pollution that's interfering.
Right. Yeah, it's a bit of both. It's a bit of both. So I mean, essentially with a whole bunch of night sky pollution, these kind of nice ellipses become not so nice anymore. and they become kind of fuzzy and blotchy, and so I mean, and so it becomes an issue of like they're not the more night sky pollution we have, the more error there is, and where we find them in the sky, and the more hard it is to figure out what energy they are and things of that nature. So
Okay.
it's a bit of both actually. So it's I mean, there's major backgrounds from cosmic rays, but also just using the atmosphere as a calorimeter, basically, you run into problems with that. So night sky is also an issue. Clouds are a major problem. There's in Arizona, the region of Arizona where this is happening. There's a monsoon season. I don't know if any of you guys are familiar with the Tucson area, but there's a monsoon season that's starts around the 4th of July and ends in kind of tapers off. Doesn't end in a bang so much as a whimper, but it goes on until September, in some cases even October. And we just shut down the instrument. We just say we give up. You know, we're not going to bother getting good data these months. It's not worth running. So there's at least 2 months a year where we just shut down. Actually, that was one of my roles on the experiment. I was the guy who actually had to fly out to Arizona every beginning of every fall and plug in all the cables.
You.
Yeah, 500 BNC cables. Your fingers get raw at the. I shouldn't say 500 times four telescopes. So I was the guy who they had the rope up and put in 2,000 BNC.
Hey Ben, you're lucky they weren't SMA connectors.
That's true.
Well, BNC connector is not the greatest connector in the world.
Yeah, we'd run into issues, especially and you'd think shutting down for 2 months and then starting it back up again, you'd think that everything would just come up exactly the way it was. No, never does. You'd get mice would chew through the cables and things like that. You find all sorts of ridiculous things. And so it wasn't, it's actually kind of fun in a way, because there's so many bizarre sort of troubleshooting issues that would that you wouldn't normally think of, that would just sort of pop up and trying to get the array started again after being shut down for 2 months.
Sounds like it's all in the infancy still.
Very much is, yes. I mean, the first detection, we're talking about maybe the youngest branch of astronomy here, except for, well, I shouldn't say that anymore because neutrinos are really getting going now. Neutrinos and gravitational waves, but yeah, I mean, considering that the first detection was in 1989, so that was within our lifetimes, Now, I should say that the field itself actually started in the late 60s. And then even before that, there were some experiments going on post-World War II. So the Whipple Telescope, which was the first telescope in the field, really, built in 1968, and they didn't get a detection until 1999. So they were out there for 20 years not finding anything.
By drinking beer and.
Oh yeah. Now, also keep in mind that this is a field that's the Irish basically invented this field. So yeah, and I go to meetings with these guys. Yeah, there's drinking.
They can pound them.
There's a lot of drinking.
So these are single malt particles.
I'll pass them along to my former colleagues. They probably like that one. Okay, so I think that's pretty much it. Conclusions, discussion. So reiterating what I've already said. So dark matter constitutes about 25% of the universe, but we don't really know what it's made of. Likely choice is Wimps, but there are things out there. And then there's this sort of three-pronged approach of accelerators, indirect and direct experiments. Gamma ray telescopes are widely used for this, and then Veritas, which is my background, has an active dark matter program looking at these various objects, dwarf galaxies, the Galactic Center, and galaxy clusters, and through cosmic rays, and which again, cosmic rays could have come from dark matter. At least some could have come from dark matter. but we haven't found any yet. And, the search continues. That's, the way science goes. And so, sort of future studies of combining data from various experiments, and then, CTA will be, along hopefully in the next 10 years or so, and they might be able to find stuff. So I'm sure they'll find stuff. Maybe dark matter, maybe not. But that's about it.
Is it hard to converge data from different instruments, and get everything to kind of line up?
Well, that's so we've kind of innovated a way where we can actually share data without sharing the proprietary information from the various telescopes. So that's still very much there are people working on it. In fact, I got an email from a former colleague tonight asking about code I wrote like 3 or 4 years ago. So I have to remember what I actually did back then. So, there's some technical challenges there, but it's actually coming along pretty well. So I think they're going to get something. I'm still in touch with some of these guys, so I think they're hoping to get some stuff pushed out over the summer. So.
Well, it's a mind-blowing thing here.
Yeah.
Ben, I thank you very much.
Thank you, Ben.
Thank you for having me.
Yeah,
Thank you.
That was,
Awesome program.
that was excellent, Ben.
Thank you.
Yeah. Well,
Any other questions?
I'm not sure I'm smart enough to ask any more questions.
What about the new physics or something?
When we find new physics, when we find dark matter, we'll find new physics. So
Yeah, I heard they got a new kind of physics that's easy to understand now.
you're not talking to the same people I am.
It's this nuclear physics they got,
Something like math.
Well, is that the one that comes in an aerosol can, Jim?
Yeah, the nuclear physics. But seriously, is there like a new physics that is possible, or is it just kind of ruled out?
It depends. So I'm not a theorist. My background is all experimental. So I guess the short answer is maybe I'm not smart enough to answer that question. But it kind of depends on. So there's various theories out there that say that there is new physics out there. I'm going back to 96% of the universe. We don't know what's going on. We don't know what's going on with 96% of the universe. So to me, in my mind at least, there's got to be some sort of new physics out there to explain this. I think there's other things that have not been fully explained by the standard model, by the rules of physics as we understand them. So my belief personally is that the new physics is out there. We just haven't found it yet. But
It's all quantum entanglement.
Quantum entanglement, I'm sure it's going to play a role in it. I'm not sure exactly what the new physics is, but quantum entanglement will play a part, I'm sure.
Well, yeah, it's funny. Just like a day or two ago, I was like browsing YouTube, looking at stuff, and I wish I'd got the link, but some guy says, "Hey, dark matter, here's the equation. It solves it all. No problem." And it explains it, and it's all figured. It shows what's wrong with Einstein, and I'm like, well, who knew on YouTube? Why don't you publish it?
I'm very skeptical of studies like that. I'm very
yeah, of course. But it was like,
yeah. You're good.
Yeah, it was just like shine a UV light at it, and you'll be free of the virus type of thing. Like.
Ben, so speaking as a scientist at heart, I would say that any overwhelming proposals, overwhelming ideas require overwhelming evidence.
Yeah.
So, just to say, oh, there's this guy on YouTube that has it all figured out, I'm going to be kind of wary and skeptical on that.
No, I think he was just all after viewers on his channel, you know.
Yeah, well, that could be.
Ben, I have a general physics question.
Sure.
I see L3 got a big government contract for a new satellite to track hypersonic missiles, and I just wondered if you could get into a little of the basics. What are the physics involved in tracking? And I don't know what hypersonic is. That like Mach 5 and above, or because regular missiles run about what, Mach 3? This is a way out of your field.
Yeah, I mean, that's not something I have any direct involvement with, and I don't know how much I'm allowed to say, to be honest.
Well, that's probably true. You ought to get a raise though anyway. So they
Yeah,
got
but it's not, but I will say it's not something I myself is purposely working on. So I'm afraid I can't answer that question.
How much processing goes on when you take readings? It must be pretty intense.
Yeah. So the data sets, so let's see here. A single 20-minute run of Veritas data is, I think, about 20 gigabytes. If I remember right. And again, that's mostly cosmic rays in there. But we actually, with the hardware, also we have hardware triggers. Let me go back to that. I can talk about that for a second. Nice thing is about the Cherenkov light, the Cherenkov technique is that you have light in this, sort of roughly elliptical pattern, and the flashes of light from Cherenkov light is also very brief. It's only on the order of a few nanoseconds, and those two pieces of information are very, very useful for us in picking out Cherenkov signals from what's normally night sky radiation. Now, I would say, as I said, to get us that night sky radiation is still, night sky background is still an issue, but we have hardware to try to reduce that as much as we can. Obviously, no foolproof because you can't reduce 100% your noise. But we have this, and this is actually something I worked on, this FPGA-based pattern trigger system to help reduce the noise coming from night sky. And then also, we also have a requirement that 2 or more telescopes have to trigger a signal before we tell the telescopes to read out the information. So without this trigger system, it'd be much larger than 10, 20 gigabytes. It'd be terabytes in the scale of a few minutes.
Yeah. So I guess you can't do subtraction of the signals against the other one, like the night sky background. You can't try to use it as a mask to try to pick out some of your information particles, or. I'm just wondering. I don't know anything.
Yeah.
About it, so.
I would say we maybe can't do that on hardware level. On the software, absolutely we can do that. And I think there are people who do that. But on a hardware level, that's a trickier game to play.
No, I assume it'd be all software, kind of like a network analyzer or something like that.
Exactly. Yeah.
Yeah.
That was actually something I was involved with a while, trying to upgrade this pattern trigger system to see if we can get in real time do better discrimination based on the shape of the Cherenkov images, but nothing ever really came of that beyond the planning stages.
That sounds similar to what we do, Ben, when we do our visual astroimaging. We take dark frames to subtract off the background, and we average it all together and subtract it off, and hopefully what's left is the real thing.
Yeah. My PhD advisor, when I got started in all this, he says, you're going to be spending a lot of your life. I think the way he phrased it is, you're going to be spending more of your life than you ever imagined subtracting backgrounds. And he was absolutely right.
That's where all the beer comes in.
It helps. It helps.
Yeah. Well, thank you for such a great program. It's
Thank you.
after 9 o'clock.
Yeah.
I think I'm gonna check out, but I'm sure there'll be other people that might wanna hang on for a little bit, so. Thanks again, and thanks for trying to take a hard subject and bring it down to us a little bit.
Yeah.
It was still hard, but it would have been miserable without you.
I
So,
try.
so, thanks
Very
again.
much appreciated, Ben.
Thank you.
Yeah, great. Thank you very much.
Thank you.
Thank you, Ben.